Okay, did it keep? Okay. Okay, so exponential and logarithms are two kinds of functions. The first one we're going to do is the exponential. That's today, right? And then the next lesson we start with logarithms. An exponential function we'll define a little bit more on the subsequent slides. But the thing to understand about both of these is it's a new kind of function. Everything up till now has been linear, quadratic, polynomial. All of those are called algebraic functions. Because in the end, you can solve them by doing algebra operations to both sides, right? You solve equations by adding or subtracting from both sides, or multiplying to both sides, or taking the square root of both sides. All those things get us towards solving for a variable when we've got an algebraic equation. Okay. These functions, you can't do that. When we try to solve things that have an exponential or a logarithm, in the exponential, the x, or if it's a variable, it's in the exponent. How do you solve for something when it's not down at the level of the equal sign, right? Or how are you going to solve for something when the variable is inside of a logarithm and you can't divide by the letters log, right? You need to have some other way to solve these things. So these are called transcendental functions. There's a few questions at the beginning of the homework, which are basically, at the beginning of every homework, there's actually like 6 questions, more like fill in the blank kind of stuff. And these are the kinds of answers I did assign those, just because they get at the understanding somewhat of what it is we're doing here. Okay. Now, remember this slide, this top of the slide, comes from the section that we did on inverses. Okay. If two functions are inverses, we know that when we take the composition of the two, right? Whether you do f of f minus 1 or f minus 1 of f, they cancel each other out, and all you get is the x. Well, it turns out that exponentials and logarithms are inverses of each other. So when we need to get a solution for how am I going to solve for the variable when it's inside the exponential or inside the logarithm, we're going to use the inverse function. I mean, the first here, when I say log a of a to the x, that's like taking the logarithm of an exponential. It's like f of g of, or f of f minus 1 of, or if I go a to the log x, that's taking the exponential of a logarithm. When you do that, in either case, everything will cancel and all we'll have left is an x. That will allow us to solve for the variable when it's inside the function. Again, something that we need to have because we don't have, we can't just isolate by doing algebra things to both sides anymore, or by factoring or something like that. Can't do it anymore. So this property right here about inverses is exactly why we study logarithms and exponentials together. Right, because we use one to solve the other. You good? So exponential functions. Exponential functions, again, that's the one we're really dealing with today. The standard form in this book is f of x equals a to the x, okay, where a is called the base. Right? And the base is positive. That's what it means to say a is greater than 0. But the base does not equal 1. But what would you have as a function if your function was 1 to the x? I mean, 1 to any power is 1. So basically, it would just be f of x equals 1. That's why we don't have, the base is never 1. It's always either greater than 1 or less than 1. but it's positive. Thank you. Okay. Okay, so we'll have exponential functions that have more in the exponent than just an x, right? It'll be some kind of variable expression that includes an x, but definitely the variable is in the exponent. Right? It's not an exponential, for example. If I say y equals x squared, that's not an exponential because it's not a variable in the exponent, right? It's not any exponent that makes something exponential. It's the variable exponent that makes it that. So the first thing we need to know is this: we need to kind of like study the graphs. I mean, what is it that we get out of an exponential function? And there's going to be two different kinds of exponentials. The first one I'm using as an example, 2 to the x. So my base is 2. Okay. Now, if you look at the graph, this is the graph of y equals 2 to the x. Would you say that it's increasing or decreasing? Definitely increasing, right? When that a is greater than 1, that's called exponential growth, right? Exponential growth means it's increasing really rapidly. I mean, and you can come across that phrase not just in a math or a science class, but just in any kind of literature or newspaper. If they say something's growing exponentially, what do they probably mean? It's growing really fast. Do they really mean exponential? Probably not. To them, that means growing fast, so they throw it out there. You could say it's growing geometrically. That's pretty fast too, but nobody says that. But they do say growing exponentially. Okay, so we're going to say that this function is always increasing, right, from here to here. So increasing over domain. Now, if you remember, we know that where we're going with this, right? We're doing exponentials and logarithms together because they're inverses of each other. But for a function to have an inverse, it had to pass a test. Do you remember what was the test that we used to say that the function had an inverse? The horizontal line test, right? You would look at this graph, which is clearly a function, right? Passes a vertical line test. But it also passes a horizontal line test because a horizontal line would only cross in one spot. So definitely we can see why this function should have an inverse. Saying that it increases over its entire domain is another way of saying, yeah, it's 1 to 1, it has an inverse. Okay, now try and imagine this y equals 2 to the x, right? I'm going to plug in values for x and see what the y equals. First of all, when x equals 0, what do I get? Right? What is 2 to the 0? Anything to the 0 power is 1. Properties of exponents. Anything raised to the 0 power is 1, which is why we have the y-intercept at 1, right? X equals 0, y equals 1. Right, that's the y-intercept. Okay, if I put in numbers that are bigger than 0, like 1, then I get 2 to the 1 is 2. 1, 2. X equals 2. 2 squared is 4. 2, 4. Right? As x gets bigger, this thing is just going to go off towards positive infinity. Okay? What happens when I plug in values that are less than 0? Right? If I put in a -1, then I get 2 to the -1, which is 1/2. So 1/1/2. And if I put in, let's say, just because we know we're doing this, -2, right? Then it's 1 over 2 squared, which is 1/4. Now, if I let these numbers, right, as I let x approach a negative infinity, is there anything that I could plug in that will make the y equal 0? Or will it just make it be a smaller fraction every time? And that's what it is. It's never, there's nothing you could ever plug in for x here that's going to make 2 to the x equal 0, right? It's not, when you put in 0, you get 1. When you put in negative numbers, you just get really small fractions. When you put in positive numbers, it goes towards infinity. So if y can never be 0, that means it can never touch the x-axis. Okay, but what do you call that on a graph when it can never touch a particular line on the graph? Right, that is called an asymptote. I don't want that color. There we go. Right, so that is an asymptote. It's a line that the graph is going to approach, but it can never touch it, right? Because that line, the x-axis, y equals 0, y never equals 0. So even though it looks like it's getting really close, it's never touching. So this line, y equals 0, is a horizontal asymptote. Right. Okay, now remember domain. Domain is x values, right? But when you're looking at a graph, what the book calls an implied domain is, it's what x values can you plug in. We're going to start with all real numbers and then take away any values of x that we might plug in that would give us undefined, right? Square roots of negatives, divide by zeros. Is there anything that we could plug in for x that would make that like a divide by 0 or a square root of a negative? And the answer is no. So the domain of this is all real numbers. You can plug in anything you want into an exponential, right? So the domain of an exponential is all reals. Also, if you wanted to write it like negative infinity to positive infinity, that's another way to say all reals. It means you can plug in anything you want for x. Okay, does it look like the range is all real numbers? Does it go infinitely up and infinitely down? Not down, right? It goes how far down? Until y equals 0, but not 0 itself. So when the range, you would say, is y is greater than 0, right? Not or equal to, because we just said it cannot touch the graph. So it's just y greater than 0, which again, you could write it with a round parenthesis, 0, comma, infinity, like that. So does it have any x-intercepts? Mackenzie? Does it ever cross the x-axis? No, it never touches the x-axis. So it has the y-intercept here. It has a horizontal asymptote here. It has a domain of all real numbers. It has a range of y greater than 0. It's always increasing, so it will have an inverse, which we'll see next class. Right, that's the standard graph of a exponential growth. Now, on this slide, I put 2 different exponential growths, just to show that there's not a lot of difference in the graph, whether or not it's a 2 as a base or a 4 as a base. Right? You don't look at that number and start changing what you're sketching in terms of a graph. It's still basically the same shape. It starts over here, approaching the x-axis as an asymptote, has a y-intercept of 1, and then it goes off towards positive infinity in quadrant 1. Right? Not much has changed. So the graph is the same in all the important details. All the things we did on the last slide. Right? At least they're all, if they're both greater than 1, right? It would be different when we get to the a is less than 1. I mean, we're going to look at, like we always do with all these functions, you know, what do we do to the graph when we add a number here, we subtract a number there, you multiply by a number there, things like that. But the one thing that you don't use to switch to transform the graph is that it's got a different base. It's all the same. Doesn't matter. And another thing to look at is what happens if you multiply by a number. And this is, last year, if you got any of this in Algebra 2, I'll tell you that in Algebra 2, the textbook that we used, they didn't use the same f of x equals a to the x for exponential. What the Algebra 2 book said was this, Algebra 2. F of x equals a times b to the x. They actually had a number in front in that formula. We're going to deal with the number in front. It's just not part of our definition of the exponential function. We'll see now what happens when you multiply it by a number. But what does it usually do to a function when you multiply by a constant? We've dealt with this with other kinds of graphs. You know, if I did the quadratic, we did that one. F of x equals 2x minus 2 squared plus 3. Right, that was a shift to the right. That was a shift of up. What was it when you multiplied by a number? What did we call it? Stretch. It stretches the graph. It's the same thing here, right? That's for multiplying 2 to the x times 3 will stretch the graph, right? It'll go up faster. What did it do specifically to the y-intercept? The y-intercept was here. Now it's here. It moved up to 3. Right? So this value right there, there's your new y-intercept, 0, 3. So usually when there is a number that's multiplying in front, that's usually the y-intercept, whatever that number is. Because, again, how do you find y-intercepts? You substitute x equals 0. Okay, well, if you substitute x equals 0, 2 to the 0 is 1. 3 times 1 is 3. So that's why that is always the y-intercept right there. Okay. Now, we will get to problems like this where you have like 3 times 2 to the x. Please don't write that as 6 to the x. It's not 6 to the x because the 3 is not being raised to the x power. Right? So don't try to combine that into a 6 to the x. It's not that. Okay, now, and this is actually the Algebra 2 way of doing it. Your book doesn't always do it this way, so I'm going to show both right here. If the a is less than 1, that's called exponential decay. If you did anything with half-lives in chemistry, then that was this. Okay. So what do we notice from the shape of the graph? Is it increasing or decreasing? It's decreasing now, right? It's decreasing over its entire domain. Okay. Which means it'll have an inverse, although we really don't deal with this as the exponential function once we find logarithms and inverses. Is there any value we could plug in for x that would make y equal 0? No. It still has the same asymptote right here. It still has that asymptote. It still has the same y-intercept, which is 0, 1. The domain is still all real numbers. The range is y greater than 0. All the other details are the same. It's just the shape of the graph has reversed itself. Right? Now, if you take 2 to the negative x, right? which is, the book is going to say y equals 2 to the negative x is decay. Even though they say decay is when a is less than 1, they actually don't show it that way. Again, if you look at properties of exponents, a negative exponent means you flip the number to the other side of the fraction. 2 to the negative x is 1 over 2 to the positive x, right? Which is 1/2 to the x. So those are two different ways of saying the same thing. In the book, most of the time, it's 2 to the negative x. So it can be exponential decay because the a is less than 1. It could be exponential decay because the exponent is negative and the a is positive or greater than 1. Either one would be the same thing. So it would be exponential decay. Okay, again, just to show you that it doesn't make a lot of difference what the base is, as long as it's decay, all the details are mostly the same. You know, this graph is the 1/2 to the x, this is 1/3 to the x. It's pretty much the same basic shape. We're not so sensitive to whatever that base is. Okay, now they introduced this earlier than they did in the last version of this textbook. And kind of like just like I'm doing it like in the middle of a bunch of graphs, all of a sudden we're doing this thing. But I just followed what they did in the textbook this way. This used to be covered more in the 4th section when it was all about solving equations. But honestly, this is a whole different animal in terms of how we solve these kinds of equations, which really don't require inverses and logarithms and all that kind of stuff. And we're going to use a property here, which is also called 1-to-1, right? That's what we call the function when it has an inverse. But we're going to use the 1-to-1 property, which is, if you look at this example here, the first one on the left, right? Can you express 8 as a power of 2? What 2 to what power would equal 8? 3. 2 times 2 times 2 is 8, right? So when you solve with a 1-to-1 property, you're trying to make both sides be exponentials with the same base, right? And usually the problems they give, it should be pretty obvious what that base is. There's not too many numbers we could use, right? Because the numbers would get way too big, too fast if we went up to like 40 or something like that. So 2 is a big one. You know, what do you think the base will be over here? 3. I mean, you see a 3 there, you should be thinking 27 is 3 to the 3rd, you know. So there's things you can do that, things you should recognize that'll tell you which base you're trying to represent them as. Okay, but now, going back to this one, since both sides are exponentials, they have the same base. What do you think we should know about their exponents? If 2 to the 3rd equals 2 to the 2x minus 1, then what can we say about the exponents? They've got to be equal, right? If the left side equals the right side and the 2's are the same, then these have to be the same. So once you get it in this format, you know, each side is an exponential of the same base, you make an equation out of the exponents. All right, take these and make an equation. And that you can solve, right? Add 1, divide by 2. And again, the one on the right, we should probably be trying to write both sides as powers of 3. Well, based on what we've already said, I mean, 1/3 by itself is 3 to what power? If it's a 3 to the first in the denominator, what is it in the numerator? -1. Right? 3 to the -1 is 1/3. So if I replace the 1/3 with a 3 to the -1, right, I'll be able to write the left-hand side as a power of 3. Now 27 is 3 to the 3rd. So we're almost there. Right, now we've got to apply another property of exponents. When you raise a power to a power, how do you simplify? What's the operation that goes on between those two? Just remember, take it like this, right? Because how do you do x squared times x to the 3rd? What do you do with the exponents? How many x's is that? It's 5. You add them up, right? But when you do x squared raised to the 3rd power, right? That's x squared times x squared times x squared. That's how many x's? 6. It's a multiply. So when you raise a power to a power, it's a multiply. So we have to multiply these two. -1 times -x is x. Okay, now again, if the left side equals the right side and they both have the same base, then what does x equal? 3 to the x equals 3 to the 3rd, so x equals 3. Done. That's called one-to-one, solving equations with a one-to-one property. And we actually have the same property applies for logarithms. When we get to the next section, you know, if we can have a logarithm on one side equals a logarithm on the next other side, then what's inside's got to be the same. Okay, back to graphing. Back to what are all the things, how do we transform functions by adding and subtracting numbers or putting negative signs in there? I mean, what does it normally do to the graph of a function when you subtract 2 inside the function? And if it helps, think of a different kind of function. What if you had f of x equals the absolute value of x minus 2? What would you have said about that shift? Is it up, down, left, or right? It's to the right. So that's to the right. Right 2. Okay, how did it change the function when we added a number after the function? In this case, if you add 3, is it up, down, left, or right? Yeah, when we added 3, that was up, right? It's plus means up, minus means down. So this one is up. Okay, so this minus 3 in the last one, is it going to be up or down? It's down 3, right? And then 4 to the negative x, I mean, if you're comparing to 4 to the x, then that's got a negative in front of it. So what is it supposed to do to a function where you put a negative in front of the variable? That's one we don't deal with a lot. Okay, let's say I start with this. Right? F of x equals 4 to the x. Okay, just like that. What would be the change in the graph if I put a minus in front of the 4 to the x? what does that do to the graph? It flips it which way? It flips it to the other side of the x-axis, right? It's what the book calls a reflection in the x-axis, right? Flip x-axis, right? Makes it go down instead. Okay, but when you put an x in the negative in the x in front of the variable, in this case in the exponent, that's the flip which is across the y-axis. Right? But for us, what does 4 to the negative x represent? The difference between 4 to the x and 4 to the negative x, one is growth, one is decay. Right? One is to the positive exponent, that's a growth. To the negative exponent, that's decay. Which kind of makes sense, because if you look at those two graphs, growth and decay, don't they look like they've just been flipped across the y-axis? They do. Right, so this is you could either call that a flip across the y-axis, or you're just going to call it decay. That you started with a graph which was decay, and you moved it down 3. Okay, so now let's look at a couple. Now, what we're interested in more than anything now is how do these shifts affect the domain and the range? These two graphs on the left, this one is 3 to the x, right? So it has a base of 3, it's exponential growth, right? It has a y-intercept, it has a horizontal asymptote along here. It has the y-intercept exactly where we expect it. And the domain is all real numbers. The range is y greater than 0. Okay, this graph is 3 to the x plus 1, where the plus 1 now is in the exponent. So what kind of a shift is it? Plus 1 inside the function? Left, right? That's moving the whole graph left 1. Okay, so you could see every point on this line is 1 to the left of the graph on the right. Right, 1 to the left, 1 to the left, 1 to the left, every one. If I take the original graph for which I knew all those details, does that change the asymptote? To take this entire graph and move it to the left one, would it move the asymptote? And here's the asymptote. What would it look like after I move it to the left one? It's the same place, right? Nothing changes. Right, so a horizontal shift of an exponential function doesn't change the domain or the range. It's still the same. The asymptote's the same. The domain and range are the same. Right? So asymptote, domain, and range unchanged. Okay, that's good. Okay, now let's look and see what happens if we have a vertical shift. Right, so here's the same 3 to the x, right? And now we've got 3 to the x minus 2, right? So the minus 2 is after the function, which is a vertical shift down 2. So every point on this line is 2 down from the gray line, which is 3 to the x. 2 down, 2 down, 2 down. Okay, so if I take this function, the 3 to the x, and I move the whole graph down 2, did it move the asymptote? If you take a horizontal line and you move it down 2, did it move position? Yes, it did, right? If you move it this way, it doesn't change the position. If you move it up and down, yeah, that's going to change the position. So the new asymptote drawn on the graph is here. Y equals -2. Does that change the domain? What was the domain before we started? All real numbers. It doesn't change anything about the domain. Does it change the range? I mean, before it was y greater than 0. What would we have to say now? Y greater than -2, right? Y greater, so it changes the range. It changes the asymptote. It changes the range if you do a vertical shift of an exponential. So the new range, this is the asymptote, and the range is now y greater than -2. And, if you're asked a question like that, don't say something like y greater than -1, because you just see the graph crossing the whole number, the integer value of -1, because that's not correct. This graph goes below -1, right? It goes all the way up to -2 just without touching -2. So don't just think in integer values, right? It's y greater than -2. Don't miss all the points in here. Okay, then we have this is an application of exponential functions, which is called compound interest, right? Compound interest is something that if you have a savings account of some kind in a bank, then you probably get an annual interest rate on it whenever you put it in. You put it in, they said, okay, you're going to get this much annual interest rate. Let's say, just for round numbers purposes, that you get 12% interest on your savings account, 12% annual interest, right? It's not like they take your money once a year. They take 12% of it and add it to your account. What they do is they take not 12%, but 1% every month and add it to your account. So let's say at the end of the first month, they take 1% of what you've got in there and they add it to your money. At the end of the next month, they take 1% of what you've got and add it to your money. The thing is that your money has already been increased by a little bit at the end of that first month. So it's not just like taking the same 12% and divide it up into 12 equal chunks. It's actually every time after that first month, you're getting the benefit of what was already added to your account. So it's going to grow faster. Compounding, the more you compound, the more money that you get. And there's a famous supposed quote from Einstein that says something like compound interest is the most powerful thing in the world or something like that. Doubtful that he really said it, or if he said it, that he really meant it. But it is something that works for us. Most people that have investments of some kind, that is a portion of what you're gaining all the time. It's the compounding that goes on. So we're going to look at a couple of formulas in which we are going to relate the amount of money that we got based on how much we invested, what was the amount put in at the beginning. That's called principal. Principal is P-A-L, it's not P-L-E. When you get a certain annual interest rate, which is represented by R, and you compound it so many times per year, okay, for a number of years, which is T years. The n times of compounding per year, I mean, most of the time, what they're going to ask you, they may not give you the n, but they're going to say, like, compounded annually would mean, okay, that's once. Compounded semi-annually, that means use n equals 2. Compounded quarterly, fourths, right, means n equals 4. Monthly compounding, n equals 12. Daily compounding, n equals 365. You think you could compound more than every day? I mean, theoretically, you could, you could compound every hour. You could compound every minute. You could compound every second. Would our money just continue to grow and grow and grow and grow? And it turns out, no, it does not continue to grow and grow and grow. It actually, there is a limiting value to it, which let me just skip over to here. This is our formula for then you have a certain number of compoundings per year, right? The amount equals P, the principal, times 1 plus R over N to the N times T. Those are all things we talked about, right? The amount, the principal, the interest, the annual interest rate, the number of compoundings, the number of compoundings, the number of years. Okay, you'll be given the formula, but you got to know how to use it, how to plug in for it. Okay, if you increase the compounding, then you keep increasing, you keep increasing. In fact, there is a limit to how much you can get, and that limit is what this formula is for. It's called what would you get if you had what's called continuous compounding. And continuous compounding, the formula is A equals P E to the RT. Okay? So now we know what the A is, we know what the P is, we know what the R and the T are. So what is this E? Okay. And E is an irrational number, right? E is like pi, right? In fact, if you look on your calculator, where do you see the pi? Pi is on the caret key right there. Look one down from that and see what's above that. That's E, okay? So E is an irrational number, which means as a decimal, it never terminates, it never repeats. I mean, if I hit the E right here and hit enter, 2.71828 ... that is called the natural base. So we will have exponentials now. We've already said exponential growth just means your A is greater than 1. Okay, that's what E is, because E is greater than 1. It's just another exponential growth model. But E is a very special and particular base, and that's why it's called a natural base. We'll see, one of the applications actually is this compound interest. The way that it works to come up with that compound interest formula. But there's other things in math and science where E and logarithms, base E, come up all the time. So we go back to our formula. That's what the E is. If you're saying, what am I supposed to plug in for E? You go to the calculator and hit the E, right? And you'll raise E to whatever power that you've got. So those are our two formulas for compound interest. This is the one you use when they give you the number of compoundings, right, per year. This is the one when they say continuous compounding. So let's do an example where we have to calculate for quarterly compounding, monthly compounding, continuous compounding. Okay, well, let's see. So for the first two, for these two, we've got to use this formula. A equals P times 1 plus R over N to the NT. Right? For this formula, we got to use A equals P E to the RT. Okay, so for the A, right, the P is 6,000. You're putting in $6,000. 1 plus. Okay, what is the R? The annual interest rate is 4%. Okay, here's an important thing. When you put it in the formula, it's got to be a decimal. You don't put in 4, you put in 0.04. All right. So you have to put in 0.04. Okay, so R is decimal percent. Right, so 4% equals 0.04. Okay, for the quarterly compounding, what am I going to use for the N? How many times per year is it compounded if it's quarterly? 4 times, right? N equals 4. And then it's being raised to the NT, so we're going to use the 4 again. And how many years is it being invested for? 7 years. 4 times 7. Okay, so all of that you could just put in the calculator, just like it is. So let's do that. 6,000 parentheses 1 plus 0.04 divided by 4 raised to the, now this is where if you're using a calculator that's not an 84, it doesn't throw you into the exponent like this one did. You need to put parentheses around the NT. Okay, you'll get a wrong answer if you don't have parentheses, if you got anybody got an 83. But at mine, it threw me in the exponent, so I can just put in the 4 times 7. I mean, you could simplify it to 28 if you want, but it won't matter to the problem. So I just put everything in exactly the way I saw it, and it says that I will have $7,927. Because it's money, you're probably going to round to 2 decimal places for cents. How many cents would that be? 75 cents, right? The 5 rounds up. So with 7,927.75. Okay, if I go to B, that's going to be monthly compounding. So what is the only thing that changes in our formula? The N is 12. Uh, 12 times 7. Again, you go back to your calculator. And I'm not going to do the whole formula. I'm just going to bring it up and right over the top of it. I just changed my 4s to 12s. Everything else is the same. 7,935 and 8 cents. Which is more than you would expect, right? More compounding, a little bit more money. Not a ton more money, but it's a little bit. Okay, the last one, C. A equals 6,000 e to the 0.04 times t of 7. Right? The formula doesn't have an n anymore. There is no finite number of times it's being compounded. So you want to put in that. 6,000. Second, e raised to the 0.04 times 7. 7,938.78. So we go, the limit, you could increase the compoundings more and more and more, but you never get more than 7,938. You put in $6,000 and it was in for 7 years, and you got back, a little bit, $1,038. No, 1,900, almost 2,000. Okay, so that's compound interest, right? It's an application of exponentials. Yep. Okay, the last problem is a word problem. It does relate to something that I know a lot of you have already done, which is in chemistry. You've probably done half-lives and things like that. Understand that in these problems, at this point in the chapter, it's not like we can solve complicated exponential and logarithm problems. All we can really do is just plug in for the variable and see what it equals, meaning evaluate. That's all we're really being asked to do here, right? And this is a real-world problem, right? Radioactive decay. In 1986, a nuclear reactor accident occurred at Chernobyl in what was then the Soviet Union. The explosion spread highly toxic radioactive chemicals such as plutonium-239 over hundreds of square miles, and the government evacuated the city and the surrounding area. To see why the city is now uninhabited, consider the model, right? So here we have a function, which is the amount of plutonium based on how long it's been since the disaster happened, right? 10 times 1/2 to the t divided by 24,100. Okay, which represents the amount of plutonium after t years. Sketch the graph over the interval t equals 0 to t equals 100,000. And then how much will remain in the year 2017? Okay, now t equals 0 is 1986. So in 2017, what will t equal? How would you figure out the t if t equals 0 was 1986 and we're trying to calculate for 2017? Subtract, right? In 2017, t equals 2017 minus 1986, which is what? 31? So we want to plug into this formula. P equals 10 times 1/2 to the 31 over 24,100. So all you're really being asked is evaluate. Just plug in that number and see what you got. Right? If you do that, understand that we started with 10 pounds. 10 pounds was the initial amount. In 31 years, there's 9.99 pounds. So how much has gone away? Almost nothing, right? I mean, the half-life of this thing is the denominator there, 24,100 years. That's how long it would take for half of it to go away. Then you'd be down to 5. That's going to take a long time. Okay. So let's see. Now, if you had to sketch the graph, some of them do ask to sketch the graph. I mean, you can enter this in the calculator easy enough. Usually it's setting the window is the thing you've got to figure out. Setting the window, they told you to use x values that go from 0 to 100,000, right? So in the calculator, I would go here in the window, 0 to 100,000. And then for the y values, you have to try to understand, okay, we started at 10, right? I'm starting at 10. So let's say 10 is here. Is that amount going up or down? It's decay, so it is going down. So actually, you would not need to make your graph any higher than 10, right? Because it's only going down from there. It's a different story if it's growth, then you've got to kind of figure, well, how big is it going to be by the end of that window? But here, it's pretty easy. You would just set it to 0 to 10, right? And then put it under y equals, and you'd see a graph. That's it. So that was it. Most of what we did today is in Algebra 2. There wasn't a lot that was different. Maybe the compound interest formulas. The compound interest formulas were in the Algebra 2 textbook. It depends on your class whether you did anything with them or not. I know mine did not, so that might be a little new. But what we learned about the functions, that part is pretty much the same. Growth and decay, domains and ranges, things like that. Right? It is kind of a different thing, the natural base of E. Right? That is an important distinction, and we see with logarithms. Logarithms of base E have a very unique place in math and science. So that is homework. Although I don't think that's correct. Just a second. I might not have changed that. 1, 2, 6. So that's correct.